Okay, so today we're taking a trip to the most volcanically violent place in the entire solar system, Jupiter's moon Io. For a long time, scientists were pretty sure they had cracked the case of its intense internal fire. The answer? A giant global ocean of magma hiding right under the crust. It really seemed like case closed. But what if the key evidence, the smoking gun, was actually flawed? Well, today we're grabbing our detective hats and reopening the case file on Io's magma ocean. All right, here's the game plan. We're going to start with the big mystery of Io itself. Then we'll look at the leading theory that everyone was so excited about. And then we're going to dig into 3 critical flaws in the evidence. Finally, we'll see what the verdict is and what this all means for this incredible volcanic world. So first things first, let's just set the scene. Io isn't just, a little bit active. This is a world whose entire identity is volcanic fury. It's constantly repaving its own surface with lava and sulfur. And just to give you some perspective on this, the amount of heat pouring out of Io's surface is, on average, more than 30 times greater than Earth's. All of that energy is coming from something called tidal heating. Basically, the immense gravity of Jupiter is constantly squeezing and stretching Io like a cosmic stress ball, which generates an unbelievable amount of friction and heat deep inside. So, what is going on in there? What kind of engine could possibly be powering this much activity? Is it a solid but sort of squishy mantle, or is it something way more extreme? Well, it turns out the clues are written all over Io's surface. In the patterns of heat it radiates out into space. And this brings us to the main suspect in our investigation, the theory of a global magma ocean. For a while there, it looked like data from the Juno spacecraft had finally provided the smoking gun that this molten layer was for real. You see, Juno has this infrared camera called GRAM, and it was measuring the heat blasting out of Io's volcanoes. When scientists first looked at the data, they found a really specific pattern. It looked like the poles had a totally different heat signature from the equator, which lined up perfectly with some of the magma ocean models. It honestly looked like the case was solved. But then, a new team of scientific detectives, led by a researcher named Tosi, decided to take a much closer look at that evidence. They had a hunch that maybe, just maybe, the data wasn't telling the whole story. And their very first line of questioning uncovered a really fundamental problem with the camera itself. Let's call this Exhibit A. The instrument was literally getting blinded by the light from Io's brightest volcanoes. Just think about what happens when you try to take a picture of the sun with your phone, right? The brightest part just gets completely blown out and you lose all the detail. Well, the GRAM instrument was basically doing the same thing. It's a phenomenon called detector saturation, and it happens when it's looking at Io's hottest, most powerful volcanoes. It's just too much light. And here's the proof. Check out this chart. Ideally, the instrument's measurements should follow that straight blue line. More heat means a proportionally stronger signal. But look what happens. Once the signal gets too bright, right around here, it just goes off the rails. It enters this nonlinear zone. What this means is that for the absolute hottest, most important volcanoes, the camera was systematically underestimating how bright they were. The core evidence was already unreliable. Okay, so let's move on to Exhibit B. Not only was the camera getting blinded, but it was also looking for heat in a really specific and, as it turns out, pretty misleading way. The camera, GRAM, mainly uses what's called the M band. It's just a tiny little sliver of the infrared light spectrum, and trying to measure the total heat using only this band, well, it's like trying to guess the full size of a giant iceberg when you can only see the one super bright little tip that's glinting in the sun. You're missing the enormous, darker mass that's actually the bulk of the thing. Now, to see this problem in action, let's just zoom in on this one lava lake, Chor's Patera. See that really hot, bright ring of lava around the edge? Now look at that much, much larger, darker and cooler crust that's sitting there in the middle. Now look at this difference. It's incredible. On the left is what that M-band camera sees. It's focused almost entirely on that bright, hot ring. But on the right, when you actually calculate the total energy being emitted, the story completely flips. That enormous cooler crust, just because it's so huge, is actually pumping out way more total heat. And the takeaway here is absolutely staggering. By relying on that narrow M-band view, the total power coming from that cooler crust was being underestimated by a factor of about 420. I mean, this isn't some small rounding error. This fundamentally changes where we think the energy is actually coming from. Okay, this brings us to our final piece of evidence, Exhibit C. This shows how just a few extreme outliers created the complete illusion of a global pattern that, well, it just wasn't really there. So it turns out the heat map of Io is totally dominated by a tiny number of absolute monster volcanoes. Get this, just 17 hotspots, that's only 6% of all the known sources, are producing half of all the heat radiance that the GRAM camera measured. It's like trying to calculate the average wealth of an entire country by only surveying its 17 richest billionaires. The result is going to be completely and utterly skewed. And this statistical problem leads to this wild result. The original studies defined polar as anything above 60 degrees latitude, and with that line, the North Pole seemed hotter. But if you just nudge that line down a little bit, to 50 degrees, the entire conclusion flips on its head. Now the South Pole is hotter. So this basically confirms it. That supposed global trend, that latitudinal pattern, it wasn't a deep geophysical pattern related to a magma ocean at all. It was just a statistical illusion, a ghost in the data, created by where you happen to draw an arbitrary line relative to a few giant outlier volcanoes. So, after re-examining all the evidence, after looking at all these flaws, what's the final verdict in the case of Io's magma ocean? The verdict is in. And based on these three pretty fatal flaws, the evidence for a global magma ocean, at least from this particular data set, is incredibly weak. The camera was blinded, the viewpoint was way too narrow, and the statistics were totally skewed by a few massive outliers. And what's really cool is that this verdict is backed up by a completely different line of evidence. A recent study that analyzed gravity data also argued pretty convincingly against a global magma ocean. It's just a fantastic example of how science is supposed to work. It's self-correcting, with different teams and different methods all getting us a little bit closer to the truth. So, while the evidence for this one particular theory may have crumbled under closer inspection, the central mystery of Io's incredible volcanic engine is still very much alive. The case isn't closed. In fact, it's just been thrown wide open again. And it leaves us all wondering, what amazing secrets will the next generation of missions to this fiery little